Hey, welcome to Coffee Compiler Club. Here today to talk about compilers and language runtimes and null and not the null and peephole optimizations and simple that are broken or not or whatever comes around. Oh, Aurora, I had an Aurora last night. Um, yeah, and we're being recorded and we'll all show up on YouTube in a couple hours and or a couple days, depending on when I get to it. And that's it. So, does anyone want to start with something, or I'll throw out my bug du jour on simple this morning, which was interesting. Just all
Yeah,
quiet things. We'll just do this thing.
start with the bug.
Um, Let me hit which one am I sharing here? We'll try, no, no, no. Hello. Zoom changed their things again. How about this one? What did I do here? Yeah, okay, so this was the test case that came around this morning. I renumbered it for people who were staring at it, so the names made a little more sense to me. There's a struct
Can you
I, which just
increase the
contains an int,
font?
struct p, which just contains a pointer to a int, a struct
Can you
I.
learn, please make the fonts larger. It's
Oh,
impossible
Yeah.
to see on the laptop.
yep, yep. Window, no, view. Somewhere under view, appearance. Hello, appearance. Zoom. So I go 150 or 200. Is this like fine or we want bigger?
It's fine.
It's
That's it. Fine.
fine. Okay,
Mm.
fine. So there's a simpler version of the same test, but the optimizer cleans it out enough that it doesn't trigger the original bug. So this is a struct and another struct with an I, and the key here is that this I is supposed to be not null, and there's no initialization syntax in simple right now. And one of the discussions we're having this morning is coming up with an initialization syntax where pre-zeroing wasn't good enough. So right now the semantics are everything gets pre-zeroed, but this doesn't say I question mark, it just says I. That means it's a not nullable and it got zeroed. So it starts incorrect, starts null, and it's a not nullable value. So there's no initialization syntax in simple. So that's sort of the default way it goes. So make a couple of these pointers in order to confuse the optimizer. And I fill one of them in with an I, and I fill it in with some interesting value. And then the other confuse in the optimizer is make another P, and this one doesn't get his I field initialized. And in fact, this one doesn't get his I field initialized, and this one does. So there's a confusion of who got initialized and who didn't. Then I grab one of the PIs, neither of which got initialized, and I grab its PI field out, which is now null because they're both not initialized. And then I load to the null pointer to get I, and I ought to get a compiler error saying this program is rejected, it can throw a null pointer. That was my expectation. And in practice, it ran into the simulator and the simulator passed the compiler, ran in the simulator threw a null pointer at runtime. It's not supposed to do that. This is supposed to be caught by the compiler. Okay, so what happened was the field type. Well, okay, so then how does it work, and I guess there's interesting questions. How does it work? Like how am I supposed to catch this? And do I have a reasonable solution? Oh, here's Yasser and James. Let me throw them in here. Sorry, I'm talking. I'm not paying attention. Da, 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 da. Um, Yeah, so all right, so summary for Yasser, who might find this interesting, and James might find this interesting. So this is a buggy program. It failed this morning in that it passed the compiler while I can throw a null, and then it crashed in the evaluator. And the complications to the program are there just to confuse the optimizer. But in the end, P1 has an I field who's not listed as being nullable, and therefore it should not be allowed a null, but everything is pre-zeroed. So it starts a null, it's not supposed to be a null. That's the current semantics. You're supposed to initialize it before you use it. Uh, the two P's here, and there's another set here, are there to confuse the optimizer. Same with setting P2, confusing the optimizer. This P1 though never had its I field set, his PI field set. So this always loads a null. So this crashes with a null pointer in the evaluator, and it's supposed to be caught by the compiler. Um, and then the bug was the PI field takes its initial type as its declared type from the I, which is declared not null, but in fact, it needs to take the greatest lower bound here so that because it's going to start null, it's not actually declared. It doesn't actually have an initial value of not null. And that means with that small change, uh, this guy is known that he might be null, and then he blows. And I do that with a flow analysis. So the typing here, well, here's another person. Intellij is coming along. I haven't seen him in a while either. Where do I have Intellij? I have to do it the hard way. I'll get him in a second. Yeah, so the typing here is simply, I'm doing a flow analysis. This is a new thing for me in a language spec. It's typing via post-optimization flow. And that's actually like the p-polar runs to completion, and let's go find that. And then I run a check to see that everyone, where's stop node? That chapter 15, you had all these chapter things going on here. So the evaluator eventually calls stop node iterate. Here, we'll just do this in the test. Parse, iterate, and then he expects to fail. So run through, get rid of my debugging hooks. Got to the type check. Okay, so how did I do this one? Did I grab the wrong? I grabbed the wrong test. Let's do this test. That's why. Okay. Parse, whatever parse does, iterate. Iterate runs the peepholes. So here's the giant work list, while work, do things. That is also running a bottom-up flow analysis in parallel with doing peephole work. So when that's done, I'm going to come back to this stop guy and run type check. This gets me the walk for error on type check, and all that walk does is call error, which you see has 3 usages or 7 overrides. Come back here, and one of the overrides is in memop, which is saying might be null. I'm going to run to it. Okay, so he hits the might be null. He's on this load I, and the load I has his declared type of, not sorry, his inputs having some prior memory state. Let me make that bigger, and some address. And the type of this address is now nullable. So the input, so pointer type, this type value is now this TMP here came from this prior load. That is nullable. The question mark against this is nullable. And that's what this test here says. Oh, you're a TMP and you might be null, then boom, I blow up on you. So that's the current way I do null checking in the compiler. It's just a flow analysis. So a better flow analysis would be a top-down version, which probably has to happen, and it's actually not very much code. But instead of doing something that sort of traditionally says, I started you with not a null, and I always only assigned you not a null, therefore I know you're not a null. I'm going to start you broken and confirm that you got fixed before I load it on you. I don't claim it's the most clever solution. It's definitely a different solution. And it allows me to do other things, like you have a null pointer, some sort of null pointer crashy code in dead code. Well, it's dead and it gets thrown away, and then I won't claim your program's an error. Is that useful? Yeah, but it does mean dead code doesn't error out here. So that fix, then, let's see if I find, it was right here. I didn't have the GLB, the greatest lower bound. Oh, here's Derek as well. I didn't have the greatest lower bound in here. So he took the type as being a not null, but there's no initialization done on structs other than zeroing. So the field type actually starts 0, So actually the loads value allowed is in fact including null. So I needed to do the greatest lower bound hack, and that would prevent the load from believing that he only ever could be not a null. And so when he loaded, he would join with what he knew to be true. So this actually gets into a whole nother realm of things here. He has a declared type from memop loads do. Here's his declared type. So this was a thing that Dibyundu asked for, and I tried to explain to him what happens here. Where do I go with how to explain what happens here? So if I start, one of the things you can do here, and this is everyone's optimizer. I'm talking Sea of Nodes, but it's everyone's optimizer. It's the same problem for everybody, or same question for everybody. What is the minimum allowed value for different nodes? You can notice that control nodes like regions and if tests and the like can either be reachable or not. But the type system all includes everything, including integers and floats and structs and memory. And an if node or a region can never be memory. It's not sensible. And the output of a store is always memory. It's never a scalar value. It's never a float. And the output of an add instruction might be an int or a float, depending on how you define yourself. But the output of an add is never memory. It's never a pointer. It's never control. So there are minimum allowed types. And one of the things you can do is say, I'm going to allow every node to take every type. And that means when I go to these sort of big algorithm switches where I do the top-down or bottom-up version, I just pre-initialize everyone to all or pre-initialize them to any, to bottom or top or whatever. That's allowed to be there. And then they'll immediately move to some more sensible thing the first time anyone does a value check on them. You ask, what is your value out? Well, it moves to something sensible. But it might, in the meantime, have like a junky thing like a bottom or a top, even though that's not otherwise allowed. And then there is another way to do this, which is say I never allow a node to contain a value outside its declared known type. And then when I initialize, I can't initialize everyone with a bulk, put you all to top, or put you all to bottom. I have to initialize you individually asking, what is your dynamic allowed range? You're one of the ints, you're one of the floats, you're a uint 8, so you're only the 0 to 255. What is your range of allowed values? Let me put that type in there for you. And that makes the initialization setup for any of these algorithms a little more fancy. In exchange, when somebody asks for a value, like load says, what is my memory input and what is my pointer input? Well, your pointer can be null and it can be a pointer, but it can't be a float. So we didn't have to validate that he's got a float input or something stupid. It won't be an all, it won't be a top, it won't be a bottom. It'll be a null or a pointer. And actually, I do nulls with type memory pointers. So it'll be always a TMP. He knows his pointer, it will always be a TMP. That is the type of this guy for a load will always be a TMP. Which means when I get into doing math on things, I don't have to do things with TMP, except I'm not doing it here. So I'm just going to find an example where I just cast you to knowing that you're a TMP. I don't have an example handy, but I just know you're a TMP. This one here actually is probably redundant and can go away because I know your memory is always a memory. It's never not. So in one hand, you get values that are wildly out of bounds. You have to check that they're moved to something sensible before you can do something sensible with them. On the other hand, when you initialize, you have to bind you to the known declared type, which is what I was doing with load. And that if he has a declared type, then I know that his output has to be within the bounds of the declared type. And that means that right here, I did a join on your declared type. I don't know what the type of memory was containing for what the field the load's going to load, but I know that when the field's done loading, it's going to be whatever type the field's going to allow to be loading. So if I'm loading a byte, by God, I'm only going to get a byte out. I'm not going to get a float out. I'm not going to get a fat integer out. I'm going to get a byte. Therefore, I can join the types. So I was joining the types, but this has to be the actual values you can get out of a load, as opposed to what the parser was declaring as the type. And the parser declared a not null, but the actual type can't be a null because I can load from an uninitialized null field. And so the load node was illegally lifting the value to be not a null. And then the second load would claim it was okay because his pointer was not a null, and it was. And so that was the crash. So the sort of the different, this is one of these, I haven't figured out a better or worse answer. Both directions seem entirely plausibly good. Either allow alls and bottoms, alls and innies or tops and bottoms, and then you have to check for them at every one of your compute calls and every one of your idealized calls. Do I have a junk input? Well, I got to wait till it settles before I can do something sensible with it. Or force everyone to always be reasonable. And then your initialization has to do some work to set them up right. And also the outputs of each one of these calls has to produce a thing which has only got a reasonable output type. So if I fail to do the join here, and also I didn't have memory state be tight, be precise, then I would propagate a bug where the load was supposed to return me something in the bounds of his declared type, but he just took it straight out of whatever the type of memory was, the contents of memory at this alias, which was not tight for a prior different bug, and then you would propagate your bug along. And so what happens then is you get these cascading bugs that you have to chase a long ways. It's difficult to chase. So you have to go nail it at each step, and then you get the bug only goes one step and you catch it. Yeah. So anyhow, Simple went with this pattern, and AA and C2 went with the other pattern. And so there were some places where I didn't get it all right. And this was one of them. And that was one piece. And I had another people error that just crashed. As soon as I fixed one bug, I got the second bug, which was a much more minor. Didn't have any deep philosophical death. It just had an easy, stupid edge walking death that I fixed.
So if I understood correctly, at each point you have to have a well-defined type. So is this correct?
Yeah, at every node, every program point, the expectation is all his inputs are well-defined, and he will produce a well-defined output. He won't produce a top or a bottom. And in fact, if you're a float node, you can't produce anything other than something in the float range. Or if you're like a narrowed integer, like a byte, a 0 to 255, your type will be that value always. And that's actually
That
only done with like,
excludes if you are specifically casting. So can you do that in simple? Can you
I
explicit
don't
cast?
have any explicit casts in simple. You can declare narrow pointers and store them into a narrowed field and load them. And that happens in chapter 15 tests, and that will cast you to a narrowed pointer. Let me see if I can find a more obvious example. Some of the earlier tests were doing things. These are trying to break me. Find a simpler test that's not trying to break me. These are array tests. What did I do? This is like chapter 14 here. Where did the narrow things come in? It's like chapter, yeah, here we go, like this. So this produces a value which is in range. This makes a value that is out of range, and add is allowed to produce an int of any value, any size. The write is supposed to truncate, and the load is supposed to sign extend. So let's run this guy. And well, he's all pointers. He's all integers. He'll fold. Let me see if I can find one where I'm doing things with the arg. Yeah, right here. Go away. So what is stop? Okay, what is this horrible thing? Uh it's just masking to the it's a bit mask. So the add one just goes for free. So add here is starting by taking, let's see, I assign arg to B. So, and so that makes a truncation. And then because it's just a local variable, there's no store to memory. So it's an actual in register truncate, add one, truncate again because I store it again into B, and then return. So you get truncation code. So that's a cast too, from a wide int to a narrow int. That's what you call it's a bit truncation cast. It throws bits away. You're trying to say, can I cast you to something weird
Let's
and
say
then know
from
that the output, so the deal with a cast is his output is whatever his cast type is to be.
Mm.
So I also get casts for null pointer checks. And that shows up. Chapter 10 is exactly doing these. Let me see. This one's an error. Who's got a cast going to be in here that's going to have a null check? That's going to be a runtime null check. Like, here's a funny case where user didn't write any casts and any null checks, but I know that you're never a null here, so I don't actually have to do anything.
So the much more tricky part would be if you allow an object as a runtime concept and then explicitly cast it to something. That would become more complicated, I believe.
Yeah, I don't know. Right. So we're type safe language, so I'm not letting you cast a struct A to a struct B, right?
But if you are object, like in Java object, you
Yeah,
can
I don't have any
cast.
subclassing. So suppose I go to subclassing, then you get these runtime tests that cast, that change your type, but they need to have a test first. So this is a code that's going to have a test. So what happens here is bar is either null or not according to arg. It's allowed to be
Yes.
null. I don't know if it's null or not. It's randomly whatever arg is on input.
Yes.
So I had to write this test or I would have rejected the program. Having written the test, what is the type of bar over on the right-hand side? I cast it to be not null. So that's
So yeah, only after the check succeeds. So sounds
right.
correct.
So here is a cast in the IR text print. I don't know, is that readable by people? Because it's a funny
Yes.
placement.
Yes. I
Okay.
can see it.
So here is the if test. And then I'm dragging the state of memory through from wherever 24 is. This is a funny place to do the print. That's why it didn't print well. But this is the cast that says, I know you're not a null. So it's node 27. So I'm gonna go over here and go find how about this time? Find 27. So 27 is a node in IR. It's a cast node. It has a type that he's supposed to cast to, void star, which is a not null any pointer. And his his output type is pointer to bar. His input type comes from his input, p node, whose type is pointer to bar question mark. So if I go look at cast node here, he's just going to do a join. This is what casts in general do. This is what join is for. Join right here. Take your input, join it with under T. So cast lifts you, and he just says, for free, you're better, except that he has a control edge, and the control edge stops you from hoisting the cast. So, and then the user of the cast is pinned behind the cast as well, which means it's pinned behind the test. So the cast here has a control input of 24. That's this block, which is actually the output of, the if test, the true side of the if test. The store takes as an input for the pointer edge 27, which is the cast. We step behind the cast, behind the pointer. So that's how you get the correctness for casting. But I can cast behind a check.
You can cast, but you cannot cast bar to an integer forever, for example. That wouldn't be
right.
illegal.
Being a type safe language, I'm not casting bar to an integer. So
yes.
you could do things like I want to say casting int to a float, but I actually have an operator that converts int to float. And I have a rounding operator converts float to int. So these aren't, sometimes in C languages they're written as casts, or Java they're written as casts, but they have a semantic meaning. So I put a node in that just says to int or to float.
Yeah, for example, in a star word, I would much more it would be more concise to say that interpret that pointer to a bar pointer instead of casting. So
Suppose I want to make a hash code off of a pointer by just taking the pointer value as a hash. then you could imagine an interpret cast that said, treat it as a pile of ints. I mean, try a pile of bits. Treat this pointer value as a pile of bits. I could write that cast. That wouldn't be type unsafe yet. It would break if I said, take this pile of bits as a pointer. But a pile of pointer bits, pointer as a pile of bits is not unsafe quite that way. It's all fine.
Yes. Cool.
Right. And now what was I doing with declared type? Oh yeah, because things have to all be their declared type. And then all the cast does is has a new declared type. And I give you for free the output of the cast here. Like if I'm evaluating the cast from a top-down perspective, I know it produces as an output at least a not null pointer. But until the optimizer runs a while, I couldn't tell you which kind of pointer it was until the value here at node 22 fell from whatever it fell to something. But node 22 comes from this fee. The fee knows already that he doesn't have to. He does though. Fee knows your type. He knows you're going to be a pointer to bar question mark.
But it cannot go the other way around from a pointer to bar to a void pointer to any pointer, or?
Yeah, well, I can no. The fee can know that he's never a question mark. His declared type or his required to be is at least a bar or null. But he could be that he computes later that he's actually always a bar and never a null. Or he could compute later that he's always a null and never a bar. So he could improve his answer.
But that's more sharp. That's sharpened type of what you already have. You cannot go from a pointer to a bar to a pointer to a void. So
yes, this guy can't go. Yes, correct. This guy can't go from a pointer to a bar to a pointer to a void because his minimum best type is known to be at least bar question mark.
Okay, cool.
But if both of his inputs turn into nulls or both of his inputs turn into bars, then he'll give up. He's got a choice, bar or null. He can give up either side.
Yes.
And then the cast will either go dead if you want one way, or will be redundant if you go the other way, and then it will fold up for being redundant. So casts have their optimization, which says I'm a junk cast because no one cares. Idealize. If you're an is-a test, you're dead.
Yes. Okay. Cool.
So the whole null pointer safety in this language is done via the flow analysis. It is not done by having a known type in the user visible type space. I go ahead and optimize away, and if that turns out to be, I can't get rid of a null into a load or store, I'll throw an error at you, and you have to say if null, do something else, and then you're fine. And then there's syntax sugars that come along later that would do things like null question, like I want to say Kotlin, like Elvis operators or whatever. Just say, hey, if it's null, leave it a null. If it's not a null, do your thing. And then you can cascade, pointer loads with question marks between them. And the answer comes back as it's either something failed along the load chain and you get a null back or default value, or it all went to the end and then you got whatever the final load is. But there's a lot of syntax sugar to go in there. So that was this morning's, bug du jour. Can you do typing systems differently? Yes. All right, somebody else's thing. We haven't heard from Yasser in a while. Yasser, give me can you give us an update?
I guess right now I'm working on linker stuff. It's almost useful. It is almost useful. I can get like Hello World linked against like libc on Windows, and then that works out just fine. And I've fixed up a bunch of crap around making sure that the data is sorted correctly, because I do all of the like processing for it basically all in parallel except for that sorting bit. So like all the exporting and all the parsing is all done in parallel. And then there's a bunch of fun bits there. And so there's a bunch of stuff around making sure that the sorting is consistent, so it actually like gives me, consistent binaries. And then the issue right now, I don't know what the issue is right now. I'm like debugging a smaller program because I tried linking against like my own project and seeing if it could like link the entire thing. That didn't work, or like it half works. It like gets some of the things. I'm thinking that there's some like relocation that's screwed up right now, but I can get like hello world and a few things bigger than that. But once I go a little bit bigger than that, I think what's going on is like something in libc is not getting processed correctly, and so it breaks everything else. I think.
I did one linker project when I was probably roughly your age, very long time ago, and got it 4-way parallel on a 4-way power PC, and a lot faster than the old linker. But this is all at Motorola. I'm sure it lived and died in the Motorola tool chain long, long ago. And yeah, it was kind of a messy thing. I don't know. Linkers have a long, long history, and they do a lot of things that seem there are better ways to do a lot of things that they have to do or end up doing.
Yeah. One of the big things I don't really like about linkers is that I think that, especially for a lot of modern languages that like compile everything as like one big unit, it doesn't really make sense to like do as many object files. Like it probably would make sense to just say, let's take the compiled output from in memory and then just export an exe. And like you can link against libraries and stuff like that. And so like that's what I'm doing. I'm like libraryifying it. So you could actually take my like backend and from the compiled output in memory, take that and pretend that it's an object file. Because all the linker really needs to see is you have sections that have symbols and relocations, and so I could make that conversion for it without ever needing to go to disk.
Right. One of the joys of JITting is you get to run your own relocation linking strategy and skip all the things you don't need to deal with.
Yeah, exactly.
And it's all in memory in the first place. It's all a lot faster and simpler.
I did just
Are you writing your own linker, or are you writing files to be linked?
I'm doing both, but right now I'm writing a linker.
Oh, okay.
Yeah.
So when you said you were writing a non-blocking hash map, right? You're using one you wrote yourself.
Yeah. Or it's a hash set. I can write a hash map, but I've gotten away with only a hash set, which is only slightly simpler. I like wrote out at some point how you would actually like extend it. But yeah.
Right.
It's all the same concept.
Yeah. You have to do another CAS on the updates for the for the map.
And then for like when I'm doing like slot claiming, I also have to in the non-blocking hash map, the slot, like the key, it doesn't really matter which key lands there. For me, it does matter which key lands. There needs to be like, if the old table had a key in there, I need that key to be migrated up because I'm doing like interning with it. But in the non-blocking hash map, the slot that would do that is the value slot. The value slot might preserve the old value, but the key could be the new key because it doesn't really matter which key is there, if I remember correctly.
You're doing well, okay, so you said some things that make me suspicious that you just blatantly broken, so I'm not reading it right.
Okay.
You're doing interning on keys as well.
So I have a hash set, so I only have keys. Or keys and values. I mean, you could technically think of them as like both, I guess.
Yeah.
And so I guess the logic is basically just find a null slot. If it's null, then if you have an old table, go search that table. If it's got the entry, then you CAS from null to the entry. And then there's a bit of like magic around that basically. But for the most part, that's like the core of the lookup and the interning attempt.
You have to have a way to say are you ever removing while this is going on? Or resizing?
No. There's no tombstones or anything like that.
Yeah, okay, fine. Yeah, that probably works. That makes sense.
Yeah. And if I had a hash map, I'd basically do slot claiming. So I'd say like, oh, cast from null to key, and then from there the slot's still empty, but it's at least been claimed. And then from there, I would fight, or like I'd have another cast that's for the like value that says like, oh, convert it from null to whatever like the value I want it to be in. And so technically somebody else could fight me for like the key could be from one thread and the value could be from another thread. But if they're both like both keys are equivalent, one of them wins the cast fight there. The other one could technically win the like value fight. But regardless of who wins, like linearization wise, you have one key and then somebody with the latest value. So like that would work out fine. And then when it's null, you have to go like migrate from or if it's null and you have an old table, then you migrate from the old table. And so you have to worry about that case too.
So your multiple threads are fighting for which is the canonical version of interned key.
Yeah.
And I heard you say is you could resurrect different threads could fight and then believe they each had the canonical key. If thread one won the first fight and said, "I have the canonical
so no,
key,"
for that would be for the map case. For the Hashset case, there's like they all get back the same key. So I basically do the decision making process. So like two threads might run, they might both check the old table, notice that let's say it doesn't have anything in there. They'll both try to cast from null to their value. Whoever wins is the one that like everyone takes that value, and the loser just takes whatever value is there.
Okay. So there's not a separate. We won in the old. Somebody wins in the old table. Somebody else comes along and queries the new table. When do you get rid of the old table?
That is a very fun process. So eventually I do the same, like copy out all the objects, but then I run into like I need to detach it. I can detach it, but other threads can still be looking at the old table.
Yeah.
So there's this nasty problem that garbage collection kind of completely hides.
Yes.
Which is so I do it with I think it's called epic-based reclamation, and the idea is that I basically annotate when I enter and exit the interning regions. And so now I just have to make sure that I'm basically like waiting for like enough of like a checkpoint to be passed. Yeah. So either I'm not in the critical sections, or I guess critical sections, like
right,
the thing that I'm annotating basically, and then if I'm outside of them, then that means I'm not loading the pointer that was just attached, in which case I don't have a reference to it, or I'm inside of one. If the number, like, it basically has a counter of every time that it enters it. So if the number goes up, then that means that I'm in a separate one than the one I checked before. And as long as I've checked and made progress, then it means that I have had to reload the pointer. And if I've had to reload it, then I know that he's not holding on to it anymore. Or that he has at least acknowledged the fact that it's been detached.
Okay. But the delete of the old table, I'm sorry, the forwarding where you quit looking at the old table.
Yeah.
Happens because at some point everyone's outside of
everyone's outside
of the mid lookup.
Yeah, exactly.
And you can now declare the old table actually dead and bump forward who's looking where. You allow nested tables, nested resizings?
No, it only has one old table. I think I tried playing around with multiple tables, but then it like seemed a little spooky, so I like decided not to do that.
Yeah, okay. Yeah, non-blocking, the Java non-blocking one does allow multiple tables. And that was the
for me
state machine doing that.
Yeah, I went with I can't remember why. I tried playing around with multiple tables, and there was some reason I remember like not wanting to do it.
It gets spooky, but okay. The non-blocking one works because I had to do it on Azul systems. We'd have these like problems where you'd have 1,000 cores would hit, table was empty, they all start inserting furiously.
Yeah.
And the table would go 2, 4, 8, 16, 32, 64, 1,000, 2,000, 10,000, and then it'd start to slow down, you know. And we play catch up and get rid of all the old tables, and you settle into a million size table after a little while, but 1,000 cores hit, the table grows really fast, and you never get to catch up behind for a while. It's fine.
Yeah, it makes sense. Yeah, in theory it should all work, because as long as I just like make sure to check the old tables and check them in order, so like I'm looking for like whichever is the latest table, which
you have hard to do. Well, the reason to roll up the tables so you quit having to check the old tables.
Exactly. Yeah, but in theory I could technically, like, it would be slower to have a bunch of old tables, but it wouldn't be impossible.
It wouldn't be impossible, right?
Yeah.
Right.
Like even technically I could actually just never detach tables, but like that would just be like, because at some point they become obsolete once the entry's been moved up.
Right.
Yeah.
They become obsolete, but you have to keep checking them until you have some story that tells you that this table is no longer got anything in it.
Yeah, like fully obsolete. Everyone's done needing to look up into it.
Yeah. I would maintain I would kill entries in the table, so put a tombstone down so no one could add a new key to an old table at some point. And count the number of times I killed an entry, and when I killed the last entry, I would declare the table dead. But
Yeah,
it didn't
so
have
I think
the GC reclamation, but I could bump where you started from. You knew you didn't have to start in the old table anymore.
yeah. So in my setup, what I end up doing is I end up doing the insertion, and if the table changes while I'm doing the insertion, I just do it again in a new table.
Right. Yeah. I think you still end up with a race where you walk away. The clock cycle after you insert the table moves and you walked away, and that's fine. It's just in the old table now. The next person who looks it up will discover it's in the old table and have to move it.
Yeah.
Okay. And hacking linkers.
Yeah. So I've ended up with quite a lot of hash sets because of that, because like the symbol tables, a bunch of like constant interning stuff, and yeah, that's it's been very helpful. And so I've got a good feeling that I could pull off the fastest linker. So now I just need to make sure that this thing is like stable and stuff. And there's a few things that like there's just so many random little like semantics, I guess, about how linkers work that I
Yes.
keep running into.
So I was trying to say earlier, they're very, I don't want to say obtuse or something, have bazillion tiny details that kind of sort of are all semi-redundant all with each other.
Yeah.
Yeah, fine.
Okay, right now I did actually find something that is concerning, which is like my main has no like my argc is 0. It's like I don't even have like a program name, which is strange. So that's probably the direction I'll take to finding the bug. Whatever that bug is.
So, but my usual story with these things is that there's 3 or 4 or 5 bugs, and they're interlocking for a little while, and you tease apart a bug, and only to discover there's another one and another.
Yeah.
So
It homes in on it, and you get it
what
eventually. Fine.
what is the scope for link time optimization? So some techniques.
I basically like don't want it, I guess. To do link time optimization, you're basically just going to need a call out to like LLVM. And so like if you look at an LLD that supports link time optimization, it's going to be like a good like 80, 90 like megabytes or something like that, because it's literally just lugging around the compiler again. I don't really want that. I also don't want it for LLVM stuff. And because I want my linking story to be, oh, you take one big module that you compile in memory, I don't really need link time optimization. You should just like, this is something I've tried to like push people to with like new languages that use my backend, which is like just compile things on like compile functions on different threads, go throw all the like function local optimizations on threads. There's like a module like a cross function stuff, all the like IPO stuff. That stuff doesn't thread as well yet because I just haven't done any of it. But at some point I will figure out like, oh, what is it going to look like to schedule these things? And there's some room for that, even if there's not like, there's a lot of the like compiler pipeline that could be thought of as like one process that does a bunch of different units all in different threads. And then you just like have this like big linker that can handle that. And you never have to make an object file. You maybe import some libraries from other people. So you might import some other people's object files. But there's no need for LTO. You just like do that all like, I guess at compile time.
Yeah, you're doing it.
Well, but I think the problem you will run into is scalability of this step. Like you may not call it LTO, but at some point where you have different like translation units all together and you try to optimize across them, that's where you run into scalability. And I don't think the fact
so
that
what
it's
I'm
done
arguing for is just like
linked-
one giant translation unit.
Yeah, and basically this, yeah, I think it's terminology question. You can call it LTO, you can call it something else, but
Sure.
the problem is it's just a lot of code, and yeah, I don't think there are like, yeah, LLVM has what it's called ThinLTO, and it does various tricks of like separating important information, analyzing these module summaries before actually doing some more specific optimizations across across translation units.
But you're running together. There is a point where you're trying to run together code from different translation units.
So there's like eventually like a hard boundary of like, oh, at some point there's like libraries and OS stuff. But like for instance, I look at something like Zig or something. There's nothing like, the only thing that makes Zig want to use multiple object files is the fact that LLVM doesn't parallelize well across one object file. So like, oh, we'll just run multiple separate isolated units and then we'll like run them in parallel. But like other than that, like they'd be better off with one object or like with one translation unit if it was able to like parallelize the way I can. And so I'd argue for them to do that. You could even, in theory, do like fancy caching stuff with that. Like, there's nothing stopping me from making a like a fancy incremental linker, where you can say, "Oh, I want to like take things in and out."
So while LLVM and other classic static compilers, they do parallelism just by using separate processes and then synchronizing like through object files. What you're
Yeah.
saying is that you want to do this within one process and then take advantage of the fact that you have stuff in memory and you don't need to at least do I/O to transfer stuff around.
Yeah.
Yeah, you'll save something for sure, but as I said, I think the main bottleneck is just the amount of code you need to deal with when you bring everything all together.
Sure.
Just need a bigger test case. You should hand them a big test case there, Arthur.
Yeah. I can't wait to once my C compiler is like completed, I will throw it at like Linux or something.
Open
That's the dream. Yeah. Oh no, you guys are C++.
You don't do C++?
No, I'm not doing C++. I thought about it before, but I decided against it.
Well, actually, I don't know these days. Back in the day, the amount of C++ we did was very small. We did templates for just square bracket array lookups. That was the limit on templates. Everything else was just, you get it in C, I want to say C11 or something. It showed up a long time ago, the different comment styles and declarations and stuff. It was very minimal C++. But I guess that was a long time ago. So
yeah, I might do like a few C++ features. Because the thing is, I'm scared of doing like a bit because then people are going to expect C++, and that's when I get into like problems where it's like, oh, it doesn't support these C++. It's like I don't really use
if you
C++.
just say C,
like,
then they're like, oh, okay, and
yeah,
you don't get bitched at. Yes, I get it.
yeah,
Wait, you're not perfect? What?
yeah.
Fine.
Yeah, but there's a few like huge C projects. So there's some room for testing that kind of stuff. And then I want to test it against well also like new languages too. Because new languages don't have to worry about the same concerns. So like I can do the multiple translation units thing. So if you pass my C compiler multiple input files, it can compile them in parallel and then compile them all into one translation unit from the backend's perspective, and then do like internal linking where it like pretends that like if you have an extern that points to another like source file, then it'll just like link them up in the IR basically. And so instead of needing LTO, it's just all one big unit. There's a bunch of fun stuff that comes with that, and I want to see what that looks like for like massive projects, and then also making that incremental because I can do that. Like the thing is in a sense the reason why we do the like the process boundary and like the IO boundary is because it's convenient. But like there's nothing stopping you from saying, oh, I mean, if I have a ton of stuff, then I can just like page it out to disk if I really needed to. And now you have more control over paging things out, especially when you don't need to page things out. Like for a lot of programs, I imagine you actually don't need to page out ever because you can fit the entire like compilation unit into memory. And then for the programs that you can't do that for, there's a lot of room for like, oh, we can manage this a lot better than if we just blindly dumped everything to disk. And so that's a lot of the space I want to investigate. I don't know, we have a lot of memory and a lot of virtual memory too.
Oh no, you don't want to go. You don't start swapping.
Yeah.
I think swap exists, but it's generally the heat death of the universe if you start to swap.
Yeah.
But yeah, I don't know. If it fits in memory, it does. That was one of the arguments I went for in a lot of different things. Actually, the old linker, I did the same argument, actually. It fits in memory, so I'm not going to do swapping.
So back to simple. Where we are, chapter 15 now, or
yeah. What's for chapter 16?
Yes. We are I believe because we are heading now on the tricky things, I believe, that require more CF node expertise.
Well, okay. So here's a set of things that are obvious candidates for chapter 6. function calls. Big one being printf or something print. But as soon as you have function calls, you can sort of write way more interesting programs. That's a big one. We can go through and I had a list here. I was just looking at the list. Somebody was asking.
Do we support function arguments? We do or we don't?
Sorry, what?
Function arguments now.
Oh, yeah, function calls get to have function arguments.
Yes.
That's part and parcel of functions. The actual parser side of parsing the argument lists are sort of trivial. The compiler has to deal with functions. Okay. Another one would be exceptions. Like I'm kind of shortcutting array range check exceptions. If you throw a range check exception right now, the evaluator blows up. Another way to say that is there isn't any range check testing. I could throw that in and then get the runtime check happening, at least get a panic if you get a range check. And then that would beg the question of, hey, doing loop optimizations for range check elimination. So function calls, real range checks exceptions followed by loop ops on them. Codegen. We schedule, but I could pound out a register allocator and a code generator in a couple chapters. Same style I did with Derek here, just this last one.
So from a CAF node standpoint, do we have all the node primitive for functions? Will be introduced?
Not function calls, but it's pretty close. Like there are things you might want to throw in as minor increments. Like we don't have a CAS operator right now in simple. We don't have any concurrency either. So yeah, fine. I think the basic node types are all there. I'm trying to think through what other things you'd expect or want. It all happens if you start to get serious about writing big programs, you discover you missed something. But it's hard to write big programs without function calls. So I'm kind of thinking function calls are next. Oh, another one would be a big pile of syntactic sugar pieces. We don't have an increment operator. You'll look at like the sieve of Aratheses or the other prime finder or square roots or whatever. I have a couple of different larger programs. Oh, and there's the brainfuck evaluator. They all desperately want an increment operator. It would cut a huge amount of work out, or text verbosity. There's no for loop. So you want to run a for loop, you say int I while equals 0, while I less than array length, blah, 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 I equals I plus 1. You need a for loop. Just for less syntax shenanigans. And there's probably a generic for loop with the same iterator runs over multiple arrays with different offsets. Like
do you already have a while?
Nice, tidy, element-wise iterator mapping.
Do you already have a while loop?
We have a while loop. The only loop we have is the while loop.
It's pretty close probably to just add for as a syntactic sugar.
Yeah, that's what I'm saying. This will be a chapter of syntactic sugar. Hacks in the parser, no changes to the nodes.
After you do functions and you are completely done with functions, then closures would be interesting.
Oh, actual real closures?
Yeah.
Oh my God. Yeah, closure. Well, okay. So closures get exciting only when you actually have codegen because they force heap allocation of stack slots. And codegen is like how you make a stack slot, right? And then there's no garbage collection support either. So garbage collection support would be another thing.
That's why I said that's why closures are interesting because they kind of force you to cover a lot of interesting otherwise topics.
Well, okay. So malloc and free versus GC. This was a very much a direction of which way to steer simple. If you steer towards garbage collection, you're immediately a high-level language. If you steer for malloc and free, you're a low-level language.
Or lifetime annotations.
I'm sorry?
Lifetime annotations and borrow checker.
Right. And then the question is there something to be done with a borrow checker that's more convenient than Rust annotations on a borrow checker?
I mean, most closures don't need to be annotated. It can be quite simple.
This is not about. I'm saying closures is separate. If I were to do closures and have them be explicitly heap or stack, I could go to like I want to say like the GCC hacks where I say you can't cheat on closures except explicitly, and you have to write some annotation that says I'm extending the lifetime and my stack frame looks like a stack frame, but it got heap allocated. And now no GC, so I still need a borrow checker on stack frames. So fuck, what's that about? Or there's GC. So I don't have an answer. I don't have a good answer. Like it would be really would be a research problem to say I want to do Rust annotations with real closures and no GC. So I guess if I go there, I'd say standard functions, no closures, and or malloc and free, either one of those, and with borrow checkers on mallocs and frees.
What do you mean by real closures?
Upwards exposed function arbs. You can return a function reference from inside another closure. What's the right obvious tiny example? I have these in AA all the time. They're the little tiny examples.
Basically, closures that allow you to escape references.
Yeah.
Okay, yeah, I don't think Rust has that.
Right. The implementation is no longer stack-based, which has all these giant efficiencies on any current hardware. So instead of being stack-based, you want to mostly be stack-based, except where you have occasionally done this thing. And it's like a generator in Python or other languages they change the name on you and they say you have to do something different in order to make it happen. Because it's this huge loss in performance. You have to ask for it. And then is it exciting? I don't know. Can you make it less of a performance hit or can you make it more obvious while still preserving things? I would claim if I was going to do real closures, I would either go down the garbage collection route, and I was kind of hoping for a low level route. So in the low route, I would do function calls, then malloc and free with some sort of annotation syntax to see if I can get rid of you having to say malloc and free. And then figure out how to apply that to a closure-like notion. And maybe you have to put an annotation on that would basically say, I'm escaping my stack frame. It has a lifetime now. I have to go annotate where the lifetime finally goes away. And then, then I do something heap-like with it. I don't know what it's going to be like. Depends on what patterns show up out of that. The other one with functions goes to subclassing and instance methods, object-oriented instance methods. It'd be another chapter question mark, like who cares which direction to go for which links. Somebody already mentioned, hey, let's do subclassing. I like virtual single inheritance object-oriented programming with virtual calls. Those both have an efficient representation, and I find it very useful. And we could totally take simple structs and put functions in them and have them be classes now. Be modest syntax change, probably needs no new nodes, just use inventive uses of nodes. It probably would helpful have certain type improvements, but not necessarily any nodes. It's just loads and stores. A virtual call could be explicitly done in the IR that stands, or we could add a virtual call knowing that if it didn't inline and optimize, it would turn into an inline cache and a hardware implementation. Does anyone have a preference then on all these things I've said, cogen, x86 or not, versus?
I say the most useful, immediate most useful things would be functions, and then
yeah, that's my theory. But there's a lot of follow-on things that sound like fun. The whole attack of sugar is easy and has.
Go ahead.
Sorry.
Go.
No, I'm just
if you
throwing
go
out the devil's advocate.
The low level with malloc and free, maybe defer isn't. I believe that defer closing, automatic closing on scope exit.
I'm curious if Simple lends itself to hooking up the Intellij PSI API so that you get an editor and a PSI at the same time. an AST can be lowered from the PSI.
I'm
from
sorry, I
the
don't have an
editor.
AST in simple.
That
Well, what's a
the
PSI?
PSI,
Sorry.
the IntelliJ internal tree that holds on to your symbols and refactors your things,
Right.
tracking type info. So
I have not looked at doing, where's Levo when you need them? I have not looked at doing a language server. So the language server shows up as one of the things. I don't have a simple mode for Emacs because I don't even know what the language looks like. I mean, and we're still adding to the language. Holy crap.
yeah, so if your emitter is figured out, then the PSI is going to do whatever cues about this piece of IR going to this, emitting use case. I don't know more than that.
Right. I don't know. I don't have an AST. That was one of the Simple's main demonstrations was straight to SSA form without an AST. That being said, can you manufacture an AST so that IntelliJ can do something reasonable? I don't know. What I would want out of IntelliJ would be debugging single step support. I find most of IntelliJ's refactorings to be mindlessly broken. They work, but they're so hard to use and so difficult that it's way faster to refactor with my existing Emacs toolchain. It has a
Do
thing
you
that
want to
says
buy an IntelliJ 10 license? It's really fast.
it's when I refactor, and it happens all the time. It's IntelliJ's offerings for refactoring don't give me the information I need to know if it's going to do the correct job or not. And the effort to validate that it did a correct refactoring the way I wanted it. So it's not just as refactoring, but I usually have to change things along also at the same time. That if it's just faster for me to run through Emacs than it is to go run through IntelliJ's. I've done it a few times. A post, yeah, hey, go do this, and it's just like brutal. I mean, it screws up.
I don't use refactorings. I just use Alt O and Alt F, find by text and find by symbol. The
Yeah, right.
refactorings are not valuable at this point in time
Right. So find
anymore.
bys, I don't know if IntelliJ needs an AST to go find by, but it may not. Certainly, Emacs has a find by that works by me. I'll just hit my button on Emacs to go find the pieces.
Yeah, those refactoring tools or anything that like changes your code, for me, I'll use them if I've checked in beforehand.
Exactly. I guess the one thing I use occasionally is I'll rename a function that spans many files in IntelliJ. That seems to work okay.
All you need is Xcode for that, but yeah, that's the main one.
Right. Okay. So can we get IntelliJ alive and well? Maybe. Do I want to do that? No. Would I mind seeing it? Yeah, it'd be great.
Is that the fastest way to the ground floor? Is that the top floor window there? The
Exactly.
PSI?
Yeah. No, I would claim, until you get like function calls, you're not writing big enough programs that matters. And my real goal with Simple wasn't to make a language that was highly useful. It was to go demonstrate a compiler. And I've got most of the parts of the compiler in. There's missing loop ops, that's a big one. And there's codegen up the backside, which isn't technically C of nodes other than it's highly convenient and it's useful for people who've never seen a backend do C of nodes codegen. Those are things, I guess, function calls. And then we kind of getting down to maybe it's time to instead declare simple ready to be turned into a book. See if there's any money to be had. There isn't.
I'm just thinking out loud, couldn't you use your existing simple parser or any C of nodes parser to make a basically what is pretty much an AST simply by turning off the peeps when you parse and also turning off the value numbering? So just like disable those things and you basically have
you don't get a tree out, you get a DAG. It's
but
ugly.
Only because of value numbering. So if you disable value numbering.
No. You don't still get a tree.
Your loops are still going to look like loopy, like cyclical.
Right. Yeah, you get to while loops and he puts fees in. You get to ifs and stuff. He puts fees in. So the deal there is it's a recursive descent parser, so it naturally traces the tree that's naturally in the code. And so you could spit out a tree node. That would be probably way the hell simpler if you wanted an AST, but it wouldn't map to your SSA nodes very closely. Not even with optimizations turned off, it'd be a closer map, other than you have this weird behavior that every time you get an if, the tree would have a tree here and a tree here, and nary the twain should meet. And in the SSA form, they all tie together at the bottoms where the tree comes to a diamond, comes right back together. And then you nest those recursively, and of course, the trees never meet, and the SSA always meets. Then you get loops for which you would have a loop header and a tree and the tree side, but on the other version, things that are only alive in the loop come around, things that are not would have escapes out, but that has no real correlation to a tree.
Okay, but yeah, I guess so. It seems like it would be close enough to do most of what people want to use an AST for, even though it's maybe not technically an AST. So I'm not sure.
Right. So if the goal is to produce a tree to be edited by IntelliJ, I would put a flag on the parser that says I'm making a tree or I'm not.
Yeah.
Or I'm making both or whatever. And then I'd feed it to IntelliJ. You're not running it. You're just feeding it to IntelliJ and doing whatever you're hacking around. And when you hit the run button, you then get the SSA version out of the same damn parser.
Yeah. Yeah.
And, the parser itself is actually, we're not parsing C++, so the parser is pretty stupid. It just recursive descent, follow it down, make a tree, or follows the tree path.
Yeah.
Okay, I'm going to do functions next, I guess, in chapter 16, but there's a lot of things that are fair game down the road, including syntactic sugars and or malloc freeze and Rust annotations, or I could be talked into doing a GC thing or CodeGen or anything else. What were you doing, Alan? You're doing structs with values.
Yeah, so if you open up the notepad, I put, or the Google Doc, whatever it's called.
Yeah, I do that.
Put some code in there.
Can you share?
I go find it. I'll go find it here.
How about my setup works, I can't share because I'm using a different computer.
Okay.
But, yeah, so it's done there. And then I guess zoom in a bit.
So struct O, struct S. Yeah, I hate the O because it looks like a 0. That's why I changed the name in my example. But that's just a bad name. So here's your constructor syntax.
I'm going to make it bigger so I can see it on any laptop screen.
Sounds good.
Okay.
Where the theory I would have is if you don't say something, you get an initial 0. And for things that can't be 0, like this OP, the parser would enforce that you did an initial assignment, but he'd have to know that you were known to be. No, he could just do initial assignment.
Yeah, here. Okay, first I'm going to change everything to T from O because you can.
Right. Wouldn't you love to search and replace in Google Docs? Jeez. Okay.
Well, there is a search and replace, but it's in this case I don't trust it.
Exactly. And then, in your example here, you do P equals T, but I could say P equals arbitrary expression that the parser can't prove is not null. So there's two proving points. There's the proving point you get when the parser proves you're not null. There's a proving point you get when the entire thing runs out of optimizations that says not null. And which one do you allow or require?
Yeah, so there's sort of two questions. One is, do you now allow uninitialized values? And so for me, it's just
I'm with the land of Java models that says there are no uninitialized values that you can use. If you end up with one temporarily, you do, but you're not allowed to use it. And the goal here
is... And this is sort of the functional school of thought where it's like, oh, well, we'll just make it required to always initialize the value, and then it's correct by construction.
Yeah, but it's not. Here, let me write you another version here.
Okay.
Who knows what an expert does, right? So just, expert here. What does expert do? I don't know. Is it null or is it not null? I don't know. The parser's ability to prove things are null or not is limited.
Okay.
So you can do this, and then the parser has to prove that expr is not null.
But I mean, I think it's a lot easier to check whether an expression is null than to check whether the control flow assigns a value to a
It's
field.
sea of nodes that turns into it's the same behavior.
Okay. Well, all right. So yeah. So okay.
So
that's actually not the difference here. The difference here is the aliasing. Let's see. So up here you have t. You're assigning it a value. And then it shows up in the other struct because the struct contains it, and you're using pointers. It's a reference pass.
It's intended to be a reference. This is the expected behavior. This is a type language with memory semantics.
Yeah, and so but then like down here, so the proposal is that you don't get that behavior because they're just values, and when you assign a value, you don't change other values.
Right, and now I would claim we have to talk about we're having value semantics. So this is not. You're right that this is not the exciting question because it's null or not. That's not the question. The question is value semantics versus pointer semantics. If you want to switch to value semantics, the pointer semantic question still shows up on the next example.
Right. You still have pointers. They just have explicit pointers. They're not implicit in every struct.
Okay. So. And now we have pointer syntax everywhere, and now we have the new syntax, which is, hey, I can have structs. They're just collections of fields.
Right. And then you have this new pointer construct, which I just sort of picked out of thin air. And that's how you make a pointer now. So if you just use new, you get a value, and you have to use new pointer to get the memory semantics.
Okay, when you use new pointer here on this t, is t live on as a value, or does it live in memory?
Yeah. So t lives on as a value. It just stays the same because it's a value. And then the pointer can be mutated so you get the sharing with the pointer, but you don't get the sharing with the value. And so the struct lives in a pointer most of the time, right? So here t.
Okay, wait, I'm missing here. So in other languages, what I would have said here was that you did this. Took the address of t, immediately implying it was in memory. You put the pointer.
No. So that's the thing. So this t here does not live in memory. It's just a value that's floating around. It's like 1 or something.
So this TP says new pointer. It gives me a pointer to what? A memory version of t? You just clone the t structure.
So what this does is it allocates a memory address and fills it with t as a value. So it serializes t to bytes, and then
I want to break this into I want to break this into 2 steps. Allocate some memory. I'm going to allocate a pointer to a t structure in memory. Mm-hmm. This t structure has some initializing constructor, which is I equals t dot I, or otherwise a clone-ish behavior. But you just cloned a value that lived in registers into memory. But separately, you can just make a t-sized struct.
Well, I mean, let's see. I mean, if you
have an initialization, you've said, let me say new pointer. Let me try new star t.
It's really like this. First, you allocate a pointer of type t, and then you assign memory equals t dot I. It's like.
Yeah, so new pointer here is what was my old new. It's allocating a memory, whereas the new here doesn't allocate memory. So I claim you don't need a new keyword if you're not allocating memory, and we reserve the new keyword for I allocated memory.
Okay, yeah, that's fair. I didn't change the name.
Here I make a struct t, and I just filled the fields in. It's a value. I just made one out of whole cloth. And here I did new. This makes me a new t, and I didn't initialize it yet. So it gets the standard pre-zeroing.
Okay.
And then you're down here, oh, I'm going to fill it in, doing however I fill it in. And, C would say this has an arrow syntax, so we go to C syntax for it. It's fine. Now you've declared S. S contains whereas S has a pointer, and you put a pointer in, and you do, yeah, okay. So this is just,
yeah, and I can take out the new.
yeah.
I can just do like that.
Oh yeah, because S is a struct. I mean, S is a memory value. It's not a pointer at all. I mean, yeah, right. So it's a linked list head and whatever. Okay, so now this particular what you're doing here is we are adding a new semantic, which is the value structures, and we are changing the ref semantics to make the refs explicit instead of implicit.
Mhm.
And then is this an interesting way to take simple as opposed to the current version where it's all ref semantics and the refs are implicit? Because there's another version that there's the fourth quadrant. We did 3 sides of the quadrant here, which is where we say the refs are what they are, they're implicit, and explicitly you have to ask for values. But you can ask for a value version.
Yeah.
It doesn't have any memory semantics, but it gets the extra syntax.
Well, and the other thing about this way is because the refs are implicit or explicit, I mean, you can take like a new int and you can say like, you can make an int pointer, for example. And I don't think you can do that in simple now because you don't have an explicit reference type. You can't say you have a pointer to int. You can only
instead I'd say you have a struct who has a single field that has int. It takes the same storage space. But I in particular, one of the things I'm doing in simple is I'm not letting you have interior pointers. And the reason for no interior pointers is there's no aliasing, and also it allows an efficient GC. We could argue that I'm not doing GC or I am.
No, I mean I agree with that. And like so in this section, like this, so this is like syntax sugar actually. This is like you read start.p and then you say like update. So like something like that. So you have you read the entire struct from the pointer, you update the value in that struct, and then you write back the whole struct. And so, and the theory behind that is that it's easier to optimize multiple reads and writes when you are writing and reading the entire struct because you have a better level of consistent semantics to value updates. So like if you don't, like if you actually update each field individually, then it's observable what time the fields are updated, and you have to preserve that in the optimization order when you're considering concurrency. And
this
so if
is
you just
so we're not doing concurrency here, but we could. So having said that,
you mentioned it as a potential chapter. I'm just listing.
No, the Java memory model has worked out fabulously well in practice. So if we go concurrent, it's totally going to be the Java memory model. And under that model, updates to fields that are not declared volatile have no ordering semantics whatsoever. And you don't get any promises. And if they're volatile, they include extra promises over normal fields about ordering.
Okay.
So if we go to concurrency, it's the Java memory model. So because you've said volatile on any of these fields, all bets are off, other than you don't get undefined values. You get a null, you get a 0, you get a pre-initialized, unless we have pre-initialization, whatever. But you can't get a have-z's updated, or you can't get a random stack garbage because something got reordered with something else. So as soon as you said memory, or as soon as I said memory and concurrency, then they're sharing in this Java memory model for how those cross. And I understand how that works, and it works very well in practice for huge counts of people. So that one's fine. It's values that are struct collections are interesting. Can we syntactically put them together in a way that's reasonable? I think the having them is not the issue. It's just, can we write a syntax that's reasonably easy to deal with? And are they more or less important than the equivalent memory semantics, which right now get the short path in the syntax? The memory semantics get the short path right now. Do we want the memory semantics to get the long path You have to say stars and addresses or whatever the new syntax is, and the structs get the short path or the other way around. And in my long years of programming, I find that the collections of structs as values are typically not as important mentally as the state. And so I want them to get the long path, and I want the state to have the abbreviated version.
I think that really depends on the programming language, because I would rarely use a reference to something in a struct in C++.
C++ has this funny thing where they blend the line, all C languages, they blend the line between who's in memory and who's in a struct that's just in registers. And if you don't take the address of, it's an optimization that the compiler does, that it just becomes a memory, and it just becomes a register thing, right?
Right.
But there's not an explicit, this is memory and this is not.
Well, there used to be the register keyword to promise that you won't take the address, but it wasn't that useful to promise.
Well, but the point is that they went to an optimization, so you can't tell. But if you didn't have the optimization, you had a keyword that said this was a value, this was not. And people for a long time honored, I fucking did, honored the register keyword. And you did the assertion check, register keyword asserted there was no address I've taken. And then internally in the compiler, I went a different route, a different path. So I claim this is a reasonable thing to expose. Register is not the right keyword. Okay. There is some sort of syntax to expose to say,
yeah, it's something like no address taken, but maybe shorter.
Well, the problem with no address taken is that if at any time an address is taken, what do I do? What do I declare as, like the proposed behavior section here, he has a struct T. Promptly, there's two versions of T. I guess in this one, there's two versions of T floating around. There's the in register version and there's the in memory version. And they're both called T. And they have different semantics and different rules of what they mean to do things. The value version wants a whole copy of the entire T object as I do updates, because semantically I'm going to treat it as a whole T. And then as Alan was saying, there's an optimization there where the update on the whole structure does field level updates only. It's all exploding registers. I don't update to one register. It's all fine. Whereas the shared memory version has obvious writes to memory that have visibility issues and so on and so forth.
Can I ask a question about your allocator, your register allocator? I know it's a borderline topic, but I pasted a link to the Captain code, C++ RPC serialization. And what it does is tries to glom everything into 64-bit registers. So if you've got a lot of bools and ints, you can, bools and bytes, like text parsing. Alan, your mic, not my mic. So it does exactly what I invented this weekend. And, I went around searching for what I did, which was take my array syntax and start coalescing the primitives into a single register I could throw around 64 bits or whatever. Maybe I'll get lucky and find a SIMD register.
What are you trying to ask?
Okay, so performance-wise, when you have a register and you're throwing around, a Boolean that you have to decode from a 64-bit long in the middle, your performance is negligibly affected, right? So is that a pretty much transparent cost if one is looking at RPC strategies?
Okay, yeah, yes and no. The extracting fields out of the middle register is really cheap. The engineering to pack and unpack has some overheads. It takes a while to get the engineering done. Once the engineering done, the performance is cheap. This is similar to strategy I did with H2O when I was serializing things to move them between nodes in a cluster. I would pack into a network byte buffer, into direct byte buffer, throw the bits of the wire and unpack on the other side, and I let the optimizer clean it up, and the optimizer did a good job. But there's a bunch of engineering work in the optimizer to do that, but that's what we're here for. So yeah. So packing and unpacking into things is very unrelated to what we're talking about here, sort of semantically.
My question is like, I hear a lot about stack register allocators.
Yeah.
And I'm wondering if that's sort of the end product of a good one.
No, that's unrelated.
Okay.
So the reason it's
the idea
unrelated
be like,
is that you've packed things into ints into an array. It's in memory. It's not in a register. It's in memory. Now the register allocator comes along and says, who's using what values to what machine instructions and how are they being done? What can I do with them? Typically, register allocator does not pack multiple unrelated values into a single register. That's optimizers doing that. Or the parser, the codegen, some pieces come along and said, I'm going to take this set of things and pack them such that I can get them all in one spot.
A premature optimization, I will say from my, I will do it. I'll call it myself premature optimizing in this area. But okay, so you're saying that's a manual thing. That's a user space kind of decision.
No, it's not necessarily manual. It's just at a different point. When you say manual, you could write that code. And I did it in H2O. I generated the code to do that. When I go look at hotspot and he's dealing with structs in memory and he has multiple small fields, I know the alignment. They do get packed end-to-end by the layout. See, Simple is doing a layout right now. And the optimizer would look at the usage patterns and the layout of things and do bulk loads and then break things apart into bytes and bits. Just exactly what you're proposing. Now, Simple's not doing that, but that could be done where, Simple had a bunch of 16-bit and 8-bit fields all laid out in a row, and he's going to touch a bunch of them. He could gather them up in one single load and then do bit masking operations to split the parts out. I would claim that's an optimizer's thing once you have a layout. Doing a serializer generally has more semantics. The optimizer doesn't get that part, but your serializer logic can pack, and then the optimizer will see, hey, I'm packing a bunch of things and then storing them down. That's all,
Okay.
grist for the middle allocator.
I'll just say that I came across this by sort of making the primitive types generic interchangeable in Kotlin. Like I just like have to throw out so much of the boilerplate language to get to something better. But in the process, my interaction with the data went down to the, everything I could look at could be stuffed in a register. So why not do that when I'm messing with the, portable number system that Java, gifted to Kotlin.
Okay.
So the primitives
context makes sense there.
Yeah. So Kotlin makes it you don't know what a primitive is in Kotlin. There's no class. There's no first class object for primitives. And in fact, there's unsigned primitives that don't even have the number marker interface because of the generics collision. So anyways, long story short, it's not a language where you want to do type conversions by reflection, or therefore in RPC make any.
In RPC, but no one wants to do type conversions via reflection. That's expensive as fuck. What the hell? But RPCs require you to serialize, deserialize, and that has some other overheads. Definitely, you want primitives if you have them to know what you're doing. So you get all kind of shortcuts there. All right.
There's no conversions in Kotlin between primitives except for
gotcha.
Hit or miss.
Okay, so I want to go back to looking at this thing here. I'm trying to figure out if there's a way. I'm getting weird lighting because it's bouncing off my desk and up under my chin. Fine.
Isn't this akin to the record syntax? What I highlighted.
Yeah, right. So what Alan said. I could argue I want a record versus a struct, or a var versus what I want a different name for something that I intend to be in memory versus intend to be as a collection. If you use the same name, then we get this other thing where uses of the named type have to have a star or an address of or extra syntax to talk about I'm doing memory or I'm just working a slice of a T.
So I remember that when you talk about records, you mean, I believe we mean value semantics. It's not.
Yeah, value semantics versus memory semantics. And I'm not saying that's the right answer. I'm just like I'm playing with Alan's proposal to come up with one that doesn't make the ref semantics eat a bunch of address of and star pointers. But maybe address of and star pointers are well understood, and we should just live with them. I don't know. And then a way that I could go there is to say, if it's going to be an in register, no memory semantics, I'm going to call it record. Nothing to do with Java records, just call it record. And if it's in memory, it's struct.
I believe there are languages that exactly call them records.
And then, right. And then, so there's always, everyone uses the same name for different things, slightly different things. And as soon as I have a struct and he contains a record, or as soon as a record, he contains a struct, I have questions, right? So a record containing struct, I think, is pretty easy. That's your example here where you have struct S has a T star. I have something I'm putting a namespace around this S thing. It's a value. It has a bunch of contents. One of them's a pointer to memory. Great. If I have a memory operation and I have a record within it, it updates to the memory involved, typically semantically updates to the entire struct. That's semantic meaning. Even though I'm updating one field in the struct, I want to have semantically a whole new struct in memory. But does that make sense to have an address of a value that is not valued or not memory, or valued or not valued, or value semantics or not?
Well, so the idea is that the pointer is the memory. Like, so if it's the T star, like it's a memory buffer essentially that stores a value of type T.
But would it be immediately representable by a memory address?
And so it corresponds exactly to a pointer, and then there's this memory floating around that you would need to interact with in order to actually access the values and stuff with the load and store operation.
So this operation here is busy saying, go update the copy of T that's in memory, but this T here is nothing to do with this T here. You made two value objects, one lit in memory, one did not.
Right. Yeah, I mean,
so this is an unfortunate collision of names. So I'm going to call this T0.
Okay.
Just to try and sort out things.
Yeah, because we broke that connection when we stopped initializing memory values in initial
right. And we could argue that the constructor here could take a whole T and that's a constructor, and he does a copy of the whole T0 and slaps it over the thing he put in memory. Now there are two versions of T, one in memory and one in T0.
Right. Well,
this updates one, and this updates the memory version. Or does it? Let me make sure.
No, well,
this S1.P goes to the memory version that got made here, and he updates it to a 2.
Yes.
So
yes. Okay.
T.I remains T0.I remains 1 because that one was in registers only, and TP.I, which however you do your semantics, the other version of this in C is you got an arrow here. I'm not claiming this is good syntax, but that one says, oh, I got updated right here. And S1 is a value, so I want to say P, but then the star dot can be like this. And that would be take the value S1, it's a value, take his P field, just slices out of a complicated multi-part piece. I took a slice out that was the P field, and then store that at 2. And then this one is your semantic update, which is saying I updated. So now this one says I'm allowed to update individual fields in a memory object, and it makes the same T in memory doesn't make a new T. I don't need, there's no update step here per se. Whereas if you wanted to, yeah, there's no update. This is not happening. Because I know that I'm updating the struct in memory when I say I equals 2.
Well, no, the idea is that it's modifying the entire struct. So like here it reads the struct T, and then it modifies its I value, and then it writes back the whole struct T.
Let me make T more exciting. It has a few extra fields.
Okay.
So the memory version, both versions have, and you didn't initialize this one, so f equals, pi.
Yeah.
Okay. So T0 has these 2 fields. This says I make a thing that's got 2 fields in memory. This says I initialize the I from the 1, and otherwise the memory guy has a 0 for the float. Okay. Here I set the memory one got a 2. Here you're saying I'm going to update. Oh, because you said P, not P.field, I want to do the whole field update. Yes, now I get you. Now you're doing a whole field update where the update is all of the prior value remains unchanged except you did I equals 2. And so F is preserved. Yeah. But you're semantically saying it's a whole field update if I do it by saying update P.
So this is a clone and an update.
Yeah.
Well, he's using an update as a word to help you understand what's going on. It's just really this thing on this left. This short bit on the left here this is a whole update to the entirety of a T. Like if I do s.p alone, I'm updating a pointer in S1 to be a new pointer to a different T object. But if I'm doing star S1.p, I'm updating all of what P points to, which is the entirety of the T structure. So I don't like these kinds of semantics, although I've seen them and used them in other languages, because they let you accidentally update all of a very large structure. In particular, in R, you'll have an array that you'll update all of the array. And then you'll bitch and moan about how slow R is. Because
so this is
accidentally made a copy of a vast, giant array of data.
Yeah, clone and then update a single value.
So more syntax that says I'm updating all of a T to avoid accidentally updating all of a ginormous T by making an entire copy.
This has two lookalike semantics to be confusing.
Yeah, now we're getting right, exactly. And now I don't like this because the syntax is like, it looks like this, it looks like that. I don't know. And I kind of went back and forth and said, okay, you can't call them all T's and have the same struct T be the memory and the register layout, and they have to have different names. One's a record T, one's a struct T. And this that seems kind of arbitrarily, it doesn't seem great to me either. It's kind of arbitrarily different between the two. On the other hand, maybe it removes some of the confusion.
But moreover, if you have a struct and a record, then a novice programmer should know the difference between them.
Once doing a register slice update, since it's all exploded in registers, naturally the slice is just updated a register. It's super cheap. And the other one is I did a load or store, and I want to have something that tells me I'm doing loads or stores.
Yes.
Versus something that says I'm just updating a slice in memory. Maybe I don't. Maybe I do.
But the whole thing drags the concept of a memory and a register in just a few keywords.
Yeah, C does this, and it does this by sort of accidentally saying if you didn't take an address, well, then you were in registers, and I know it's cheap. If you took an address, then I try to guess places where you did and you didn't take an address, and I get this aliasing thing where sometimes it's in memory, sometimes not. Or I'll put it on the stack, which is fairly cheap. And then loads and stores are all going to be L1 cache hits and misses, but I had to stackify it because I wasn't quite clear. But then I have lifetime issues and shit going on that are like bad.
So if you say one of these structs is in a register, if the register allocator way down the line can't get a register for it, is that like an error?
Oh, no.
At you?
Right. No, that one is, there is a finite count of registers we run out. We go to stack slots, which are known to never alias. And the optimizer can juggle who's in a stack and who's in a register for free, not for free, but very low cost because he knows there's no aliasing.
Okay. Well, I mean, it just seems if you're differentiating in your syntax, whether it's a register or not,
I'm
the
differentiating.
programmer's counting on that being a register.
Yeah, the cost model is very close to a register because under high volume uses, the allocator will get you a register. So you'll have some spill code. So I said struct t as a float. Okay, suppose I put 99 more fields here. Okay, it's not fitting in register. It only got 16 or 32 or however many. Okay, fine, it gets spilled. Okay, but each individual piece's parts got spilled to some independent stack slot. They're completely unaliased. They're completely independent. I can do whatever I want, and the allocator will pick the hot ones to be in registers. So you'll mostly get register costs if you're doing a register version. That's what an allocator does. Okay, then that's what it's for. So that leads me down to, and this is Alan's question, what is the semantics? Well, those memory semantics are very interesting. We'll want those. The register semantics have their own, it's a namespace for a series of values. I said struct t of int I, float f, blah, blah, blah. But maybe I really just wanted to have an I and an f and a blah, blah, blah. But I had too many of them, so I needed t.I and a t.f, so I just don't have so many to track on my head all the time. It's a nice namespace thing. Okay. That one I find useful. Now, can we blend the two such that it's obvious that I'm talking about the namespaced version of I and F, or I'm talking about a memory updates for which there's a side effect that will be visible much, much later by an aliased pointer. The whole point of the side effects is both. It will be aliased, and the bitch is it will be aliased. And can I say this is a pointer load and this is a register slice? So where's a pointer load? He's got stores but no load. So here's a pointer store, extra syntax, and here's a register update, no extra syntax. And can I do something? And then this is the danger where, oh, I made a copy of a 99 field thing. It's a couple kilobytes in length. It's one line. It looks cheap and easy. It's super expensive. I did this a few more times and I'm dying in allocation costs and overheads. So I don't want to do that one accidentally. Right? That's the whole pointer update. Well, okay, so I can have some syntax that's special for whole struct update memory because that's a copy. In other languages, they just disallow this and say, you put the copy word there. I did something where I said, copy it in. I might have to drop my curtain here. I lifted it for some lighting and the sun's moving and now I'm just getting blinded. Let me switch. Oh, look at that. How about that? I'm not blinded so much. So I claim open question. I don't have a clear answer. And I'm interested to figure out how to do this. The actual, this is all about syntax in my head. The actual compiler doesn't. At chapter 15, we're doing memories. Even chapter 10, none of this changes anything in the back end or the nodes. This is all about what the parser does. And in particular, there's aliasing stuff that goes on the memory that doesn't require a memory edge and an alias number. Because the parser will just break this out as 99 independent fields, and they'll just be unrelated independent fields. And in fact, you said here, and then of course, if you come along and say, well, I have a T1 is equal to a T with I equals, I equals 2 and F equals whatever, and however my 99 fields, the parser will break them all out into separate fields, and you'll get 200 fields in the parser, all independent. And they'll all be SSA'd unrelated to each other, and they'll all flow through unrelated. Perfect aliasing, never a question. You'll just explode them all into individual parts in the parser. They all become effectively registers at parse time.
Oh, yeah, because it would be troublesome if multi-threading is involved, but we don't have threads, so.
Right, and then you get the following thing. Now you get an expensive thing. If some random thing here Then I say T1 is equal to T0. Okay, what's the cost of this op? Well, it's the cost of copying 99 things. So, I mean, a fee function is not terrible, but it doesn't, you rapidly can stack costs on your shelf by moving value objects around that are large. Nonetheless, value objects, especially in the small, are totally useful. Pairs, complex numbers. I'm doing pixel slapping on a canvas. I have an XYZ. I have 3, not 99. I got 3 things. Oh, fuck it. I don't want to deal with breaking them apart or worrying about costs. I just want to move it. So I do understand that maybe I'm pushing too hard on the cost model piece and we should do it anyhow. And if you write this code and type T is big, you got a big cost. And if type T is small, you didn't care. This type T is RGB and an alpha. It's 4 bytes. It fit in a 32-bit register. It's kept in a 32-bit register in the end by the optimizer. The cost of the T1 equal T0 is a red move. Fuck, nothing.
But
right?
When we say it has a 99 fields, we assume they are like in an array of 99.
No, people are stupid. You write Java programs that have 99 fields. I see doing C2, doing JBoss, WebSphere. I inherited 15 layers deep in the class hierarchy. There'd be fucking so many fields. These objects would be huge. Happen
But
all the time in
You
Java.
mean like that the parser will treat that we'll explore it in a 99 fields, but
Yep.
will be treated them as one
From the parser's point of view,
one after the other. So
yeah, from the parser's point of view, the register, the value semantics are just a namespace, and he'll just that would be the obvious thing for the parser, just explode the namespace. We could have the parser not, but then the parser has to have a bunch more handling for partial updates and the like that he's not well geared for, and that does turn into expensive semantics. That gets the unavoidable cost model. So the normal thing I would claim the parser would do is just explode all these fields out. That's just a namespace. Fine, done. I think it's a convenient namespace, but it's a namespace. Bam. Okay. Now moving on past the namespace and ignoring cost, do I want extra syntax for doing memory versus doing namespace register or value semantics? Or do I want the extra semantics go on the value semantics and the registers? Good. I guess, I don't know. I can be talked into doing pointer math. I want to hear from, well, Talia and Zemilia both have been hacking pretty big on this. So I want to hear those two minimum about what they think about changing the syntax to be namespace things. I'm sorry, pointer spacing semantics. Who cares, right? Does anyone care? Alan cares. He wants pointers to pay the syntax cost and values not.
Yeah, well, I kind of see it as an experiment. I just want to know, like, is it actually simpler to do it like this way with the structs as values, or is it simpler to say, oh no, structs are just, this implicit pointer thing? Like, I don't know which one is actually simpler.
Who uses it? What's your use case? I claim that for any program of any size, you go to memory and you're using memory things all the time, and you occasionally have these values things. Now, the occasional value things are fine, and if you labeled them, so if struct T got labeled record or got labeled value, it would be very obvious what you meant, what it was. And if you did a thing like this, you might imagine there's a cost because you're doing a 99 field copy. But if you do a thing like this, you're darn certain you're getting a copy because the value T is labeled as a value. And the obvious semantics here are, I lifted up the entire thing, I updated it, and I wrote back down an entire thing. And in your particular case here, there's an obvious optimization where I just update in memory. And in the general case where I say star P is equal to something fancy schmancy, like I don't know what it is. The obvious cost here is that I took a 99 field thing and I copied it, but it didn't fit in registers. So I took a bunch of bits and parts that were splattered about in the register allocator and tried to fold them as huge kind of copies. Or I gave up in the register allocator and I just took the struct and I spilled it in its entirely onto the stack, and I have a stack flavored version of it. And I still do a 1K stack to memory copy or whatever. there's immediately an opportunity to get big. If this gets big, there's immediately cost opportunity. On the other hand, I said value, and so I knew the semantics changed on me. And if I said, oh, the count of bytes in here is 4, 8, I don't care, and then the allocator doesn't care, and the register and the parser just explodes it all out, and it's all good. And if I went to 99, I know I pay a cost. So, you know, I'm kind of like, where do you put the keyword? And if I put the keyword there, it's here's a version of your code using keyword that doesn't. And by the way, the new sum pointer int here has an easy answer where I just demand a struct. And now you can get that one with a pointer to S would have no overhead over the thing. So is there, if I say I have a value and I want to have a memory version, the S guy doesn't have a version, so there's 2 different T's here. One of the things I'm arguing out is there's 2 different T's. There's the value T and then there's the memory T. And you know, I don't like the duplication for sure. And then this becomes, well, it's a memory key, but this is a value.
Just gonna point out that there's one data point, Hilo is worth looking at. It's a language with value semantics by default, but it doesn't really have heavy annotation burden, and it does allow in-place memory mutation too.
Say that again. You're saying simple currently has allocation, in-place memory mutation. You had something else you said I missed.
I said one language worth looking at is Hilo. It's based on Swift, but without implicit copying. And you only really have an annotation when you want to do an explicit copy.
Yeah, I'm looking for only, you know.
Like when you have the matrix, for example. Go to the subscript example and scroll to the matrix. So right, members subscripts. You can imagine you have a matrix which is 3 by 3, and you would like to in place mutate that matrix because you don't want to, of course, copy or carry this as a value just to change something. So you add a subscript member function, and then in the main function you can just get at this row and column cell, and you can mutate this in place, but at the same time the entire matrix still has value semantics. So it's kind of interesting because it may be like having a cake and eat it too. And you don't really see any heavy pointer annotation anywhere here, even though you do not have to pay cost for copying. So I think that's an interesting experiment that they are doing.
Well, as soon as you have updates to the thing, your value semantics are weird. Well, you're doing partial updates to values.
Yeah.
Which semantically would be a new value, but mechanically you know that it's in place, and no one can get at the old version anymore.
Right.
Okay. That's interesting.
Yeah, so that's, I mean, that would be where you'd explore these optimizations in simple, as you'd say, oh, well, I have these values, and so I can optimize them.
I wasn't looking for
copy on write sort of things.
Yeah, I wasn't looking for the optimization per se. I was looking for the semantics that made sense in whatever way we were writing things, you know, whatever order, however we're writing it, semantics that are easy to read and sort of easy to understand.
Yeah, because like right now you have like NT pointer, which isn't right because the star constructs. Let's see, the star here is a type constructor, so it turns a value type into a memory type.
Oh yeah, down here I don't claim this is the correct answer. I was me trying to sort out what happens if I demand a different name for a value and a memory.
Mm-hmm.
And then I don't need the star here because it's known to be in memory.
Right.
Okay, and then we're missing the update pieces where I say I have an S. I have an S is S1 is equal to an S, and I need to initialize P to be something. And as soon as I need a new P here. So then I have a TM, and I want to say, oh, geez, thank you. Wow.
I don't think you have to like type it and then go back and edit it, I think.
Okay.
No.
Yeah, I got it. I got it. Uh-huh. Okay. So I have some sort of, I mean, I don't claim this is a good thing or whatever. I'm mixing curlies and opens and everything else. And then I'm trying to say, you know, S1, ooh, what? Is a subscript one? How did I get subscripts?
All right. But I wanted to point out though here, so here, see the thing about making a TM is it has side effects. You have to use the control, you have to use the memory. So it actually it isn't as simple as just writing TM. So like a value type is very simple to construct, but an MT or a TM or whatever it is, you know.
I'm right. I didn't have a new here because I allocated.
Yeah.
And the reason I didn't have a new is because I didn't need to have the keyword new. I never had a need to have the keyword new, but it's a nice bullet point or eyeball mark to say, hey, you're doing an expensive thing or doing a funny semantics thing. You know, we could argue back and forth, hey, C Arthur, back and forth on whether we want the new keyword. But the implementation where the parser builds the structure, has all these extra edges, that's done already, and it's not very much work. So I'm okay with having being an allocation or being a value. Either one of them requires some parser work. The one piece for the memory has been done. The other piece for the value is not, but it's not a lot of work. Okay, that's not the question. The question here is, as a programming language, do we like this language or not? What do we do with, how do we treat value versus memory references? Here in this one line, the first dot says, I have a struct, I did a register subreference. Probably that certainly turned into no loads unless the spiller had to spill. But it turned into a register reference directly that just peeled out something. And then this dot I probably turns into a load unless the optimizer can get rid of a load via some other optimization, or it's a store. So one of them is a register reference and one of them is a memory reference. And here I'm using the same syntax for both based on typing the value type versus the struct type to know whether I'm using a load or a memory reference. And I have side effects that are visible or not. I have sharing or not. Now, the one you have up here has arrows, or I put the arrows in, has stars and parens, which the parens are nasty and large expressions. So then you get to the arrows, and that's a C-like flavor that says, hey, there's a memory reference going on here. And then if you use a dot, like here, there's no memory reference. That's strictly a slice of the existing structure. No aliasing, super cheap, no reference semantics. Okay. But if I do reference semantics, I have to do an arrows, or I have to do dots, or I have to address of. I need some sort of extra syntax. Here I don't because I'm doing it here, and I don't know if that's good or bad, and that might be bad too.
And I think you could overload the dot. So like if you did like a T star and then you did a dot, it would resolve properly. But I mean, it would complicate the parser a bit.
Right. Well, that goes back up to here where we have a star. And I can tell that the star is working because this s1.p yielded a value which is of type pointer, and you're writing to star pointers. You're writing to all of a pointer. And here, the arrow says I'm not writing to all of a pointer. I'm writing to one piece of the point of that thing. And your original code you had here was star of s1 of p dot, which was, we could argue, was the same thing. This equivalent here. Another star of s1.p dot I. Now you have this funny thing that says this is all of a t, however big it is. This is a pointer, I'm sorry. This is all of a t, however big it is. Update one field of however big that t was. So I'm okay with these two being the same. It's just that parens suck in writing this in bulk. And that could be the argument right there. As soon as I do this and I have to write parens, there's no syntax for not using parens. That tells me I'm doing an expensive thing. That's I eyeball and said I am copying all of a large value object. I don't know. I'll tell you what, it's time, it's noon. I want to break.
Okay.
Eileen, this is an open question that we can argue about more. There's a couple people's opinions other people's opinions I like to see. We could go either way, and until you go some way, and then people code in anger, you can't hardly know whether you did a good job or a bad job. Till you code in anger, it's not like it's fun or it's whatever. You're imagining castles in the sky and trivial examples. And the fuzzer gets you horrible examples, but there's no code a human ever writes. But if you write actual code, you can see, oh, this worked well or it didn't. Let me throw out the largest actual code example I have from simple. Not here. Where is share of? We'll do off of Intellij if I can go find it again. And let's see here. I have one or two big ones here. And actually the brain fuck is the better one. Okay, so here is the largest example I have in simple code right now. Let me do this. So up through here, we're looking okay. Here I would love to have D++, D minus minus, data of D++, data of D minus minus. I think this is legit because it's a simple interpreter that it looks like this. Here is begging to be a for loop. And, and I guess this is all begging to be a switch. Command is 62, it's 60, it's 43, it's 45, it's 46, it's 40. It just wants to be a switch so badly. Here, by the way, you don't need to equal 0. That just comes out naturally here. Do it that way. But, you write what code that looks good to your eye. Again, pluses are not there. So in this guy, I don't have any complicated structs, but that's actually, so it's not a fair treatment for, I guess the other one I have a sieve of Rathces is also just arrays. I don't have a large complicated program that's human written that does things with structs where I might start to argue I want to have memory or not. I have some trivial examples doing linked lists, but they're too small to count here. Sieve of Rathces, where that one is here. Is another array-based one that badly wants a plus or a plus equals operator, but doesn't do anything with structs. Okay, so I don't have a good example that showcases value structs where I want to have value structs versus want to have memory and then argue it looks prettier one way or another on the syntax. In all of these cases, because we don't have good, easy struct manipulation, maybe, I don't know, want to have plus operators and for loops. I think, is this guy really? This guy, yeah. Oh, yeah, this is another for loop opportunity. For j equals to j squared less than arg, j++. Obviously, here's a for loop, although it's one line either way. It's not terrible. Here's a plus. This is a plus. Anyhow, so, future work.
By the way, Cliff, if you are doing pattern matching, there is this new paper that came out that basically unifies this with traditional branching. It may be worth a look.
Oh, another, throw
it
it
should be in
into
Google Docs, the ultimate conditional syntax.
Yeah, right. Pattern matching is one of those syntactic sugar things that's really useful. I would totally willing to get syntax sugar. My cat just woke up and realized he was all alone except for me. So come find out he's not all alone. Anyhow, would love to switch if or switch. The if's pretty short. I'd be willing to, I guess, where's Simon? He had a canonicalized if that was also a switch syntax. Oop. Okay, cat.
So yeah, they are basically using if for everything, and this if also allows pattern matching.
Well, I need a while loop.
I'll take a look at that paper. I think it's pretty cool.
And then I want a for loop or a do or something. So things to argue about on Discord, what I want to call it, but it's been fun. And
but do we really need loops if we have recursion? You are doing function calls after all.
Yes. Fuck it.
That should be a short, non-controversial topic.
I don't have functions, so no recursion. Neener. As soon as we get functions, we get recursion. Oh god! But
and then you don't need loops anymore. Of course,
there are certain codes that are still usually simpler to read and understand in loop form, not in recursion form.
Fair enough. Can always have goto.
Yeah, I didn't find need for gotos yet. I do have continues and breaks, but only out of one level. I don't think we do multi-level breaks. You need a multi-level break, write a function.
C recently added something like that.
Did they?
Yeah, you can break out to a named label out of a for loop.
Yeah, you have to put labels in then. I'm willing to forego multi-level breaks with labels and do something different there, including demand you just write a fucking function call, including inline functions. So in the realm of adding functions, there's anonymous functions. And probably I'll go straight to anonymous functions because they're just so trivial to write and implement. If there's no type inference, they have to be typed arguments. Anonymous functions are easy. Fine. All right. Till next week. It's been fun.
Bye.
Bye-bye.